So let's move on to our second topic, which take the rest of today, and that's rapidity divergences. OK, so when we were talking about SCET1 and we were talking about loop calculations, we saw that there was a subtlety where when we were doing our collinear loops, it could double count the ultrasoft loop, if you remember. So kind of schematically, I could say that this true CN was a sort of a CN naive minus a CN zero bin. So you could do a calculation ignoring that, but then you have to be careful, and there's a subtraction, and that subtraction avoids the double counting with the ultrasoft, right? So if you think about there being ultrasoft amplitudes and collinear amplitudes, this avoids a double counting. Now, we never talked about whether there's something analogous to that in SCET2, and we just did a lot of SCET2 examples without ever even saying those words. So why it's actually, for what we've talked about so far, OK to ignore this issue. But in general, it's not OK. So if we go back to our picture of the degrees of freedom in SCET2, have this hyperbola, and you could have softs, you could have some collinears, and in the example that we just did, it's like these were kind of the relevant modes, and in general, you might have some guy down here as well. So these are the degrees of freedom in the SCET. And effectively, what's happened is, if you want to think about double counting, you're sliding down this hyperbola. So this hyperbola is kind of at a constant invariant mass, say lambda QCD squared, or could be lambda QCD. And unlike the case in SCET1, where this guy lived on a different hyperbola, here, to get between them, you would be sliding down the hyperbola at fixed invariant mass. OK, so that's a little different. But in general, in SCET2, there are also zero bins. So in general, you would have something like, let me denote it this way, Cn minus Cn soft. And what I mean by this is my original amplitude, where p mu is scaling like q lambda squared 1 lambda, sort of the original. And this would be a subtraction where you take that amplitude and you make it scale like in the soft regime. So it would be p mu lambda, lambda, lambda. So that's different than the example of SCET1. In the SCET1 case, we would really just be scaling down the 1 and the lambda so that they would be both of order lambda squared. Here, we're actually scaling down the 1 and scaling up the lambda squared to a lambda. And that's the right thing to do to go from here to here. So we're just taking the amplitudes in this region and subtracting them in this region. And in general, we do have that. But actually, that's not the real complication that shows up in the SCET2. The real complication has to do with whether there's any divergences associated to that. If this amplitude here didn't have any divergences, it wasn't kind of log singular, then you wouldn't really care about doing these subtractions, because then there would be no infrared singularities that you're double counting, and it would just be effectively a constant. And the constants are always ambiguous, so whatever mistake you make in constants here, you just make up by changing your hard matching. So you don't have to worry if when the collinear goes down into the soft region, there's no divergences. And that is actually what's happened in all the examples we've treated so far, that when the collinear goes into some region where it's not supposed to have singularities, that you just end up with no singularities. There's no log singularities. OK, so far, there's no log singularities from the overlap regions. But that's not in general the situation, and we'll do an example in a minute where there are singularities that overlap. And the true difficulty here is the following. If you think about what's separating these modes, you might draw lines like this. Okay, just to draw some straight lines separating the modes. And remember that we're plotting here in the p minus p plus plane, and that fixed p squared is like fixed product of p minus p plus. So p squared is p plus p minus, up to the p perp squared piece, which we're ignoring. So you could think of these lines as lines of constant p plus over p minus. Okay, and if this is the so something orthogonal to p squared. All right, so that would be one way of thinking about it. So you need something that's orthogonal to p squared in order to distinguish these modes. And the real issue with that is related to the regulators. When we use dimensional regularization, it turns out the dimensional regularization is not sufficient to regulate a divergence that would happen when the Cn comes down on top of the S. And the reason is because dimensional regularization regulates p squared. It regulates, remember it's a Lorentz invariant regulator. So it's regulating Lorentz invariant things like p squared, not something like the rapidity, which is this p plus over p minus, that you would need to distinguish these modes. So invariant mass does not distinguish the low energy modes. So rapidity you could define as, it's usually defined this way. So exponent of 2y, where y is the rapidity, is p minus over p plus. And if you look at the scaling of that, that's scaling like either lambda minus 2, lambda 0, or lambda squared for the different cases for Cn S and Cn bar. So it's this variable that's really distinguishing the different modes. Okay, and that's these lines, these orange lines, are just putting dividing lines between these in rapidity. Right? Okay, so there's a complication that dimensional regularization doesn't suffice. So you could think of it as regulating p Euclidean squared once you do the Wick rotation, for example. So it separates hyperbolas, but it does not separate modes along a hyperbola. It's a way of regulating singularities between hyperbolas, but not along a hyperbola. So that's one complication. We'll need an additional regulator. And we'll see that that regulator will eventually lead to a new type of renormalization group, flow, which is flow along a hyperbola. It's not a flow in invariant mass, but a flow in rapidity. Okay, so let's explore what can happen in an example where there are these divergences in sort of the simplest possible example. So there's enough going on that we want to make our lives as simple as possible. So what I'll talk about is something called the massive Pseudocode form factor. So you should think of it setup as follows. We're going to consider a form factor, and it's going to be a space-like form factor. So it's a space-like quark-quark form factor. Q of the photon here, space-like. And we're going to think about, rather than having photons or gluons, we're going to think about massive gauge bosons. So this is going to be some kind of Z, if you like. It could be a Z boson. And I'll just call the mass M. OK, so the thing that I'm going to want to iterate is like the mass. Rather than doing QCD, I'm doing electroweak corrections. Electroweak corrections from a massive gauge boson. So this is relevant if we have electroweak corrections in a situation where Q squared is much greater than M squared. And we're not going to be having gluons. Instead, we'll be talking about these massive gauge bosons, multiple Z bosons, if you like. You could also put the W's in, but let's make it simple and just talk about Z's. OK, so let's do this example. So in the full theory, you would start with a vector current, say, and you'd want to match that onto SCET. Before we do that, let me just write down a kind of full theory object using Lorentz invariance. So you could think about the quark form factor. And for massive gauge bosons, this is just some form factor that you can calculate. It's a function of Q squared and M squared. And then there's some spinors. And so really kind of the dependence is encoded in this F, which is a function of Q squared and M squared. M squared is acting kind of like an infrared regulator, right? So this Z boson, there's not a soft singularity associated to it. And so what you'd like to do in this process is factorize Q squared and M squared, i.e. expand this thing in Q squared and M squared and maybe some logs of Q squared and M squared. So we want to factorize some logs. OK, so what are the type of degrees of freedom that we could have here? So lambda is going to be M over Q, mass of the Z boson over the energy scale of the collision of the gamma star. And if you just look at the Z boson, then it could be collinear or it could be soft. So it could be actually 3 different possibilities. And I could think about doing this effectively in a bright frame, just like we did earlier. And then what you would have is that the collinear guy is like the quark, and then the anti-collinear guy is like the outgoing quark. So I'm calling Q of p bar. So you'd be making a transition in this diagram from n collinear objects to n bar collinear objects. And you could likewise have a Z boson, which could be collinear. Or you could have a Z boson that's soft. And you have a soft rather than ultra soft because of the mass, right? If Q times lambda is M, and so if we want a propagator that's like p squared minus m squared, p squared better be of order m squared. That happens for softs, not for ultra softs. So that's why we have softs. And the same thing for collinears, p squared's of order m squared for these collinears. So it's really an SCET2 type situation where the hyperbola is just set by p squared of order m squared. We have our node sitting on that hyperbola. OK, so it's exactly of this type over there. And the thing that's new in this example is that we're going to encounter these rapidity divergences.
Can you imagine there's the only quantum particle in your theory is the Z?
Yeah. Make things as simple as possible. So you could talk about mixed sort of electroweak and QCD, but yeah, we don't. Let's make it. In some sense, that's kind of just like mixing a problem that we already would know how to deal with this one. So let's just deal with this one. All right, so in terms of the external quark momenta, we can therefore kind of treat them as follows. Let's just let them have a large component. They're massless particles. So this is P, this is P bar, and these guys are massless. Should have said that. And if you go through the kinematics, q squared, which is minus p prime squared, if you square that, you just find it's p minus p plus. And we're just effectively, if we pick the bright frame, which is what we're going to do, each one of those is separately, I keep calling it prime, call it bar. Each one of those is separately q. Okay? The large, these guys are just fixed to both be q. All right. So we could factorize this current with these degrees of freedom. The quarks are collinear, so at lowest order they just become a Cn and a Cn bar. And then we have to address that with Wilson lines, and we know how to do that, so let me just write down the answer. We could again follow our procedure of going through SCET1, but it's now so familiar we just know what to write down. Okay, so the current would look like that. And I'm not going to worry too much about the Dirac structure. So I won't worry, for example, about gamma 5s. And we could put that in, it's easy. So that's the leading order current, and then we'd have leading order Lagrangians, and we just start calculating. And if we calculate what you would expect from a matrix from that is you'd expect that f of q squared and m squared is going to split up, given the degrees of freedom we have, into some kind of hard function, and then some kind of amplitude for the collinear parts, and then some kind of amplitude for the soft part. Okay, so you'd expect some hard times collinear factorization of the form factor, and this is what we'll be after. So it's always good to sort of have an idea where you're going, and that's where we're going. So let's consider just one-loop diagrams. And it suffices in order to make the point just to consider the most singular one. So I'm going to consider So there's various loop integrals that you could have to do when you're doing the diagrams, if they're fermions. Let's just take the simplest, which is a scalar loop integral. And I'm going to contrast how that scalar loop integral would look if you were doing the full theory calculation with how it would look in the effective theory. And then we'll see where the divergences come from. So you can think about this as the kind of the piece where the numerator is independent of the loop momenta. So the numerator just factors out. Okay, so if I took our vertex triangle diagram over there, then a piece of it where the numerator is trivial and factors out would look like this integral. So let's just study this guy. If we did this integral in the full theory, this would be both UV and IR finite. So this is just giving you some result that involves logs of q squared over m squared. So it does have double logs of q squared over m squared and single logs of q squared over m squared, but it's perfectly, there's no 1 over epsilons. So now let's think about what would happen in the effective theory. So we have a kind of analogous loop integral for collinear, where the gauge boson is collinear. There's some numerator, but again, I'm not going to worry about. If this numerator is constant, it's effectively the same constant in the case of if you take the leading order numerator in the full theory, it'll be the leading order numerator in the effective theory as well. But the denominators do change. And so if we took the n collinear, then, yeah, so this guy doesn't change, because that's just like saying p minus and k, or p minus and k minus are of the same size. But this guy does change. Okay, so this guy would be k minus p bar plus, because k minus is big, and p plus is big. Both of these are big. So both of those are big in this diagram, and so that's effectively the Wilson line diagram. Okay, where the propagator here was off shell, got integrated out, and just became iconal. And the k squared is smaller, so we don't keep it in the leading order term. Analogously, for in bar, it's the other way. So both of these are big, and this one remains, and then they're soft. And in the soft case, what happens is that both of the propagators end up being iconal. So and in our SCET operator, that's a diagram where we have our collinear lines, and then we have kind of a self-contraction of the S. But we're taking an Sn with an Sn. We have a contraction that's like this. Right? Of two of the Wilson lines, soft Wilson lines that are sitting in that operator. That's a non-zero contraction. That would lead to a diagram. That would lead to this amplitude. All right, I'm going to leave a little space here because I'm going to add something in a minute. All right, so how do we see that there's a problem with these integrals, that they're not regulated by dim reg? Well, you could look at the soft integral, and you could just do the perp. The perp is only showing up in this k squared minus m squared, so you get something by doing that. And so if we do the perp with dim reg in IS, we would end up proportional to something that's dk plus, dk minus, k plus, k minus, minus m squared to some power of epsilon, divided still by the factors of k plus and k minus. So you see that the invariant mass is being regulated. We just did the perp. Perp is gone. Plus times minus is being regulated, because plus times minus, if it plus times minus grows large or grows small, it would be regulated by this epsilon. But either one, plus going large or minus going large, or plus going small, minus going small, with plus and times minus fixed, is not regulated. And that's the rapidity divergence. If the invariant mass is fixed and k plus over k minus goes large or small. So let me write it as k minus over k plus going to 0 or going to infinity. Let me say with k plus times k minus fixed. And diverges as these things happen. And if you think about what's happening in our picture over there in these limits, it's exactly a situation where this x here would be sliding up or sliding down. So in one of these limits, this one's going towards Cn bar, and this one would be going towards Cn. So it's exactly a region where you would be overlapping, sliding down the hyperbola, and the integral has log singularities. So this is exactly a situation where we can't ignore the overlaps, and we have to worry about them. Okay, so we need another regulator, right? Dim reg is not enough. We have to do something else. So what could we do? So there's lots of different things that you could do. One thing is you could just sort of put it in some plus something in these denominators. That's called the delta regulator. K plus plus delta. That's one choice. We'll do something a little bit more dim reg-like, okay, which makes it sort of easier to think about the renormalization group. So one choice for an additional regulator is the following. So if you think about where these divergences came from, they came from the Wilson lines. So what you really need to do is regulate the Wilson lines. And you can do that as follows. Let me write out the Wilson lines in our kind of momentum space notation. So we have some n dot p type momentum for the soft Wilson line and an n dot as field. And really, it's this 1 over this iconal denominator that's giving rise to these denominators here that are giving rise to the singularity. So if we want to regulate that singularity, we need to add something. And we could do that as follows. So this is the regulator we'll pick. And I'll just write everything as kind of a momentum operator. So I've just stuck the z momentum in and raised it to some power. So pz is the difference between p minus and p plus. And that seems kind of arbitrary, but that'll do the job for us. You can motivate why you want to do pz. So this is 2pz, actually. You can motivate why you want to do pz rather than something else in the following way. And it's a true fact that once you have enough experience, you realize it's good to use pz because pz doesn't involve p0. And the softs don't really make a distinction between any of the different components. And if you put in p0, something that involves p0, that would be dangerous. So this is nice because there's no p0. So it's the combination of p plus and p minus that you can form that doesn't have the p0, which is energy. And remember that the poles in p0 are related to things like quarks and antiquarks. They're related to unitarity. So not messing up the structure in p0 means that you'll be fine with unitarity, fine with causality. You're not messing up a lot of nice things about the theory. So if you do put p0 in, then you have to be careful about those things. So if you just arbitrarily put in some power of p0, then you'd have more trouble. And so that's kind of why we're avoiding it and just putting in pz. For the collinears, we can do something similar. But for the collinears, we also have a power counting between the minus and the plus. So for the collinear, we can still make the power counting OK by thinking about putting in pz, but then just expanding it to be a p minus. And that's true up to power corrections. And we don't really need to worry about power corrections when we're regulating these divergences. So it's just putting in the large momentum. And so W, written in a similar notation, so I'll explain what the other things in this formula are in a minute. But the important thing for regulating is that we have some factor. In this case, it would be a factor of n bar dot p. Sorry?
Not eta bar dot p.
No, it's supposed to be an n. Looks like an eta. Too many variables. There's the eta. So there's some factor raising, again, the iconal propagator, sort of mixing up with the iconal propagator. In this case, it's even more obvious that it's just regulating that iconal propagator. OK, so if we were to do that and go back over here and put the regulators into these integrals, what would happen? So here, we get an extra factor, k minus to the eta, and so that would regulate this k minus. And these integrals will also have poles from the 1 over k minus. You could think about, well, okay, if we did those integrals, we'd also have rapidity divergences that are kind of the analog ones and the linear sectors to the soft ones. Here we have 2 propagators, and so if I have 2 soft Wilson lines, and so I get 2 factors, but I've conveniently chose it to be the square root, so it comes out kind of looking the same here. So one thing that is just a part of this regulator, which actually I don't know a good argument for, is kind of a priori from the symmetries of the theory, you might like to argue that that should be eta over 2. And this should be eta. But it's really just it's just a choice convention that we've made, as far as I know. There probably is some nice deep argument for it, but I don't know it. So what are these other factors? So nu is like going to play the role of like mu, right? We've changed the dimension of the operator. We compensate it back with nu, just like we were doing with mu. We're going to get 1 over eta divergences, which are like our 1 over epsilon divergences. And we're going to get logs of nu, which are the analogs of logs of mu. And that's the sense in which there's kind of an analog of this setup with our usual dim reg setup. In order to have a full analog, we should think about having a coupling. And so that's what this W factor is. You can think about it like there was some bare pseudo coupling, which is really just 1, but just imagine that you're switching from bare to renormalized in order to set up a renormalization group equation. And then this guy here, which is in eta dimensions, if you like, would have a renormalization group which would say nu d by d nu of this W of eta nu is minus eta over 2. Sorry, this is eta over 2. So that's the analog of saying mu by d mu of alpha is minus 2 epsilon alpha. It's the analog statement. I think this is okay. So this guy here is like a dummy coupling. And the boundary condition for it after you've carried out this is just to set it back to 1. So it's identically 1. It's really just a bookkeeping device. So it's a dummy coupling once you go to the eta dimensions, but you just set it always the renormalized coupling is just identically set to 1. And identically setting it to 1 is what you need to sort of keep gauge invariance in these Wilson lines. It turns out actually that this regulator here is gauge invariant, though it doesn't look like it, right? We've modified the structure of the Wilson line in some kind of way that looks like it might be drastic, but actually these factors here are still leave a gauge invariant object. So
Can you write these Wilson lines in position space nicely?
not that I know of. Yeah.
I think maybe we should if they're gauge
Maybe you can, yeah, but it's not. Since it's not, yeah, I don't know what it would look like. You could Fourier transform that power. I mean,
Without the regulator, it would look nice.
yeah. Yeah, I'm sure you could probably just Fourier transform that. I'm just not sure if it would look nice. Yeah, it might not look too bad. Yeah, and it might actually be a nice way of saying what I'm about to say in a less nice way, which is, if you look at the gauge symmetry, why is this not messing it up? So one way of thinking about that is just to look at general covariant gauge. So note, the 1 over eta and eta 0 terms are gauge invariant. And you can think about that by just going to a general covariant gauge and seeing the parameter dependence drop out. So for example, at one loop, you would take g mu nu in the contractions and replace it in general covariant gauge by some gauge parameter, general covariant gauge, k mu k nu over k squared. And you'd like to see it independent of this. But this eta to the 0 piece is kind of independent of that for the usual reasons. And the 1 over eta term is independent of that because this guy actually doesn't induce any rapidity singularities. What happens is that if you have an n dot k, then you have a corresponding n mu in the numerator. And so basically what happens is you get an extra n dot k in the numerator. So anytime you have a 1 over n dot k, you would get, for this piece, multiplied by an n dot k upstairs. And so this is canceling, and you don't have a rapidity divergence in the c-dependent part. So that's why this is invariant under the gauge symmetry. And then because of this boundary condition, the kind of cancellation of the c-dependence in the order eta to the 0 pieces kind of works out in the standard way. Okay, so it gives you an idea of why it's gauge invariant without giving you a kind of full proof or anything. So we have both 1 over epsilon poles and 1 over eta poles in general, and we have to understand what to do with them. So here's what we're going to do. For any fixed invariant mass, it turns out that we can have these 1 over eta poles. And the right procedure for dealing with them is as follows. First, you take eta goes to 0 and deal with these new poles that you have introduced in your amplitude. In order to deal with them, because you can have them for any invariant mass, you actually have to add counterterms that can be a whole function of epsilon, where you haven't expanded in epsilon, and then divided by eta. So let me abbreviate counterterm as CT dot. Then, after you've done that, you take epsilon goes to 0, and you find your 1 over epsilon counterterms. Okay, and this is the correct way of doing it. And we'll see how that works in practice in a minute. So let's go back to our integrals that I've now erased and just write out the answers for doing those integrals with this regulator. And I'll also make them fermions, so I'm putting in the numerators. We wrote them down for scalars. The scalars were the most divergent integrals, actually. I can include the numerators. That doesn't really change the story. And I can include the prefactors as well. And I'll kind of write things in a QCD type notation, even we can imagine that it's a non-abelian group. Just so CF is the whatever group it is, it's the Casimir of the fundamental. Whatever group our gauge boson's in. So here's the eta pole. It has a whole function of epsilon in the numerator, and it's even divergent. So this is 2 eta. And then the rest of it I can expand. So there's going to be a 1 over epsilon times the log. When the log replaces that 1 over epsilon, then I can start to expand, and I get another 1 over. When the log nu replaces the 1 over eta, I can expand this gamma. And it gives me a 1 over epsilon. And there's also some other pieces. 1 over 2 epsilon, and there's a log u over m. And there's a constant, and I'm never going to write the constants. So let me write all the results, and then we'll talk about them. So IC in bar is the same. The only difference between this is that P minus goes to P bar plus. It was really symmetric. And then IS is different. So the 1 over epsilon, 1 over eta pole comes with the opposite sign, and it also comes with a factor of 2 different. And in this case, there's actually 1 over 2 epsilon squared term. So there's also a double log of mu over m. And then there's plus constant. OK? And so you could think about adding them up. And what happens when you add them up is you have 1 over 2 eta, 1 over 2 eta, minus 1 over eta. And so that 1 over eta poles cancel. And that's exactly what you'd expect, because in the full theory, the eta was something we introduced in order to distinguish these effective theory modes. It wasn't something that was there or needed for the full theory integral. And so you don't really, you'd expect that it's sort of, that there's a corresponding regulator between the two sectors so that when you add them together, that the dependence on that parameter is canceling away, because it's just an artificial separation, if you like, or a separation that we're doing. So if I add them up, 1 over etas cancel, and so do all the logs of nu. Alpha I'm left with a log of mu over q, 1 over epsilon pole, double log, some types of single logs, there's another type of double log, so it would look like that, all the new dependencies canceling away. So sort of various things, which we'll start talking about now and we'll continue talking about next time. So the rapidity 1 over eta divergence, which we can call a rapidity divergence, cancels in sum. And of course, so does the log nus. And that's as expected. And if you add an overall counter term for the entire thing, it just involves the hard scale, log mu over q. So if you were to think about there being some Wilson coefficient, which is sort of C bar is ZC minus 1. C bar is ZC C renormalized, then ZC and the C renormalized only involve logs of mu over q, which is the hard scale. Okay? And that means that our hard function, which is the Wilson coefficient squared, if you, well, just the Wilson coefficient in this case, is only a function of q and mu. Okay, so integrating out the hard scale physics didn't know about the separation. The separation was really something that we needed to do in the effective theory to distinguish the Cn and S modes. And you can see why we needed to do it if you look at these answers. Because if you look at the types of logs that are showing up here, in this case, we have a nu over p minus, and in this case, we have a, is it nu over mu? Make sure I got that right. I guess it is. In this case, we have a nu over m. Okay? We also have a mu over nu. And so the sort of right scale, in order to minimize the logarithms here, we're going to have to, again, as usual, take different values of mu and nu. Well, it's the same value of mu. All of them are m. But it's a different value of nu, because it's the nu that would need to be of order q here. P minus is q. And the nu would need to be of order m here. Okay, so it's the nu that distinguishes the modes. So the logs in Cn are minimized for mu of order m, which says being on the hyperbola, but then nu should be of order p minus, which is q. And that's precisely actually where we put the x in our picture, if you think about it. OK, so that's saying that we have a large p minus momentum, and we're on this hyperbola where p squared is order m squared. And it's likewise for the other pieces. So for the soft piece, so for the, say for the other collinear piece, we need the same thing. And then for the soft, we need a different value for this new parameter. So having this regulator is behaving like dim reg, where we needed different mu's when we had different hyperbolas. Now we have different places on the hyperbola, and we're tracking that with the new parameter, and that's showing up in the logarithms. And if you think about what the logarithms are doing, you can see that when you combine terms, let's see, if you look at the 1 over epsilon, and the mu's are canceling out, you're getting a mu over q. Yeah, that's maybe not the best example. Look over here. You have this log of m over q, right, in this kind of complete decomposition. The way that that logarithm here gets made up is by having m over nu and nu over q. All right? So in order to get this log that doesn't have any mu's in it, mu is not telling you that there's that large log, but there is a large log. So there's large logs associated to these rapidity divergences. And what we'll talk about next time is how you do the renormalization group with the diagrams like this, how you write down anomalous dimension equations. There'll be anomalous dimension equations in both mu and nu space. So we'll have to move around in that space and see how it works to sum the large logarithms. But I'll postpone that to next time. So any questions? OK, so the general idea is really, as usual, it's just that now we're dealing with a situation where there's two regulators. And they're actually independent regulators. One, if you like, is regulating invariant mass, and the other is regulating these extra divergences. And so we'll be able to move around in the space without any worrying about path dependence, for example. We'll talk a little bit about that next time in this two-dimensional space of mu and nu. But you can see, just from looking at the logs, as usual, you can see where you need to be. And you can see that you need to be in different places for the different modes in order to minimize the logs of these amplitudes. And if you do that, then there should be some renormalization group that would connect these guys. So there should be some RG that goes between these guys, and there'll be an RG in this new parameter.